The Russell Hobbs K1 kettle turned boiling steam into its own off switch. Water reached the boil, steam escaped through a controlled opening, and heat moved a bimetallic element. That movement tripped a switch and opened the heating circuit. The kettle did not merely make hot water. It used the physical consequence of boiling as feedback that the task was complete. So the person in the kitchen no longer had to stand beside it and decide when to cut the power. The exact object is documented with useful caution. Russell Hobbs identifies the K1, introduced in 1955, as its first automatic electric kettle. The Science Museum Group catalogues a Russell Hobbs electric kettle made circa 1955 in the United Kingdom. The museum date is approximate, and its short catalogue entry does not publish a teardown of the switching assembly. Those sources securely identify the product and period. They do not justify invented production totals, household anecdotes, or claims about every internal part of the museum's example. A later patent by William Morris Russell supplies firmer engineering detail for the company's automatic kettle lineage. U.S. Patent 3,026,402 claims priority from a British application dated April 16, 1959. It describes an electric kettle with a heating element, circuit breaker, steam path, and two heat-responsive systems. Steam from boiling water heats one bimetallic element and operates the circuit breaker. A second heat-responsive arrangement receives heat conducted from the element and interrupts power when too little water is present. Because the filing follows the K1's introduction, it is evidence for a documented Russell kettle mechanism, not permission to label every patented detail as an original K1 component. The feedback chain begins with resistance heating. Electric current passes through a resistive element, converting electrical energy into heat. Water absorbs that heat until boiling creates a sustained supply of vapor. A vent directs some vapor toward a temperature-sensitive strip made from bonded metals that expand differently when heated. The unequal expansion bends the strip. In the patented arrangement, that deflection moves a plunger and an over-center switch actuator, separating electrical contacts so current stops flowing to the heater. Each stage converts one form of information into the next. Liquid temperature becomes vapor flow, vapor becomes strip motion, and strip motion becomes an open circuit. That is a control system built without software. The water itself generates the signal only when boiling produces enough hot vapor in the intended path. The bimetal does not measure a digital temperature, and the switch does not need a clock to predict how long a particular fill will take. A small volume, a large volume, cool water, and warmer water can take different times, yet the cutoff still responds to the event. The system's intelligence lies in choosing a physical signal tightly connected to the desired result. The over-center action matters because sensing and switching are different jobs. The strip responds gradually as it warms, but electrical contacts need a decisive change between carrying current and interrupting it. The patent's toggle spring and actuator translate a small thermal movement into a snap between stable positions. Manual reset then closes the circuit for the next boil. This arrangement does not require the sensing strip to carry the heater current itself, and the patent describes adjustment so the mechanism can be set to operate at the intended point after boiling begins. Automatic shutoff changed the human routine more than the basic heating process. Earlier electric kettles had already moved heat inside the vessel, but the ordinary job still included listening, watching, returning, and switching off. Forgetting could waste energy, continue boiling away water, and expose the heater to a dry condition. The K1's promise was narrower than complete safety under every failure. It removed routine judgment at the boil. Later protection against dry operation addressed another condition through a separate heat path. Keeping those functions distinct makes the engineering achievement clearer. Before automatic cutoff, boiling water was a short task with an uncertain ending. The user filled the kettle, connected power, and stayed alert for sound, visible vapor, or a change in the water's motion. The heater did the energetic work, but the person remained the sensor and controller. Automatic shutoff moved that final decision into the appliance. The time saved in any one boil could be small. The deeper change was that the user could direct attention elsewhere without making a predicted boiling time part of the routine. The switch works because boiling creates a new and useful signal. Hot water alone is not enough. Vapor must reach the sensing path. In the 1959 Priority Russell patent, steam passes through a vent and strikes a return bent bimetallic strip. Heating deflects its free limb, moves a plunger, and pushes a switch actuator over center. The contacts open and disconnect the element. A later Russell-Hobbs patent describes the same design logic with a sealed vapor tube directing a steam jet toward a bimetal-operated switch. These patents document the mechanism while also showing that its details continued to evolve. The appliance depended on more than its cutoff: a metal vessel, electrical insulation, an immersed or vessel-coupled heating element, plug and socket, earth connection, seals, handle, lid, vent, and switch housing all had to manage water, heat, electricity, and repeated handling together. The patent deliberately separates the heating element assembly from the removable switch housing, reflecting manufacturing and service concerns as well as operation. Automatic behavior becomes credible only when the surrounding parts keep steam on the intended path, water away from live connections, and the contacts capable of interrupting current repeatedly. The economic value of automation is easy to miss because the sensor is passive and the action lasts seconds. The product does not replace the kettle, the energy supply, or the act of filling. It removes supervision at a repeated transition point. That reduction in attention can matter every time water is boiled, especially when the alternative is abandoning another task to monitor the finish. The sources do not provide a verified price comparison or sales total for the K1, so its market impact should not be converted into invented numbers. Its observable success is the survival of the automatic function across later kettle designs. The click of an automatic kettle became a social cue as well as a mechanical event. It tells people nearby that the water has boiled and that the element is no longer drawing power. Yet the machine does not choose the amount of water, fill the cup, or judge the drink. It automates one boundary in a larger domestic sequence. That narrow scope is why the design feels trustworthy. The user begins the operation, a physical event ends the heating, and the product offers an audible change of state without pretending to understand the purpose of the water. The original K1 form did not need to remain in production for its central idea to spread. Russell-Hobbs' later patents show continuing work on vapor channels, reset behavior, switch mounting, and dry boil response. Other manufacturers developed their own controls, while cordless bases, concealed elements, molded bodies, filters, and temperature selection changed the surrounding product. Replacement was therefore inheritance rather than rejection. The visible kettle could become lighter, cheaper, cordless, or digitally controlled while preserving the same expectation. A basic boil cycle should terminate itself. Manual and stovetop kettles still reveal the boundaries of the automatic promise. A whistling kettle signals but does not normally disconnect the heat source. A saucepan can boil water with almost no specialized mechanism but requires closer attention. Temperature selecting kettles solve a different problem by stopping below or around chosen targets, depending on their sensors and controls. These alternatives are not failures to modernize. They trade electrical dependence, automatic cutoff, precision, durability, cost, and user control differently. The K1's historical importance lies in making one of those trade-offs feel ordinary. The Russell-Hobbs K1's durable legacy is event-based appliance control. Instead of asking the user to estimate time, the kettle reacts to evidence produced by the process itself. Modern automatic kettles may package the sensor differently and add separate protection, but the underlying promise remains recognizable. Start the heat, wait for the boil, and trust the circuit to open. That promise turned the finish from a human judgment into a machine state. The old stainless steel body became a museum object. The quiet expectation it established now disappears inside the click at the end of an everyday task.